Hello. So last time we had seen how to prove the existence of limits by using definitions, that is by using epsilon. For example, we had proved that 1 by n converges to 0. Okay, we had also shown that 1 by 2 power n converges to 0 by using epsilon. But whenever we try to prove it in that way, we first need to know what this value, what the limit is. Okay, then we can only prove it. How exactly do we find out this limit? Okay, we need to have an intuitive idea. Okay, so without that intuition, okay, we cannot proceed with the proof. Okay, but suppose you know the value of some limits, can we calculate other limits? Okay, these are the theorems that allows us to do that. If we know the limit of xn and if we know the limit of yn, then we can easily calculate limit of xn plus yn, which is just x plus y. Okay, similarly you can put with minus over here, it will only be x minus y. Similarly, if you multiply them, xn and yn, it will be xy. Okay, just multiply the limits, and xn by yn, it will be x by y. But over here you must know that y should not be equal to 0. Okay, otherwise you will be dividing by 0, which is impossible. Okay, so these are the theorem on limits. Of course we will do the proofs of them also, but we will do that later on. Okay, for now let us see how to calculate limits by using these theorems. Okay, so what actually did we do? We actually calculated limits by using epsilon only for the simple cases. Okay, for the harder cases, okay, the theorem on limits will be very much applicable. Okay, but always remember that in case you cannot do find the limit by using the theorem of limits, then again you will have to have intuition and then prove it by using the definition, that is by using epsilon. Okay, so with that being said, let us just jump with the first exercise. Okay, the exercise is find limit n tends to infinity n square plus n plus 1 by n square minus 5n minus 3. So this is very simple. What exactly will we do here? You notice that on top it's also a polynomial, in the denominator also it's a polynomial. We just have to take common the highest power of n. Okay, for example here we will take common n square. Okay, so you will be left with 1 plus 1 by n plus 1 by n square. Similarly over here, the highest power of n, it is n square, 1 minus 5 by n minus 3 by n square. Okay, so you can cancel them. You will be left with this. Okay, so if we use that the third rule, we can actually put the limit on top and then the limit on the bottom as well. Okay, and then calculate the limits individually. Similarly, you can split this one. Okay, but it is too cumbersome to write. We can just think of substituting n equal infinity here. Okay, just again as a note, just see that if you put n equal infinity over there, you will be having infinity square. Okay, not possible, but we can have an idea of what is happening. Infinity square minus 5 times infinity minus 3. So over here, this one, it will be positive, which is infinity, and over here also this one dominates 5 infinity, because if you square it will be much bigger. Okay, so over here also will be infinity by infinity. Okay, so we'll be getting something like this. But notice what happens after we have done those steps. If you put n equal infinity over there, you will be getting 1. Limit of this one, we had proved that it is equal to 0 by using epsilon. Similarly, we can do the same for this. It will be 0. 1 minus 0 minus 0. So the limit will be equal to 1. Okay, so this is the final solution. Okay, now let us jump with the next exercise. number 2, limit n tends to infinity, n square plus n minus n. Again, over here, if you put n equal to infinity, you will be getting root in, okay, you will be getting, this one will be very huge. So infinity minus infinity, okay, do not think that it is 0. Okay, it may have some other values, okay, because this is not defined, okay, doesn't have a unique value. All right, so let's do it. We can first rationalize something like that. So we'll multiply the numerator as well as the denominator by the same factor, which is this factor. Next, we will use a minus b, a plus b in the numerator. You'll be getting n square plus n minus n square. So you'll be having this. And over here you'll be getting n square plus n plus n. Okay, now we can calculate them. We can easily take common the highest power of n. Okay, but before that, this one we will leave it as it is. Over here we can take common n square. Okay, I'll write down one more line so that you'll be much more comfortable. Okay, so this one we can do it like this. Root n square will give you n. So you'll be having root 1 plus 1 by n plus n. Again, we can take common n. Okay, so I'm writing so many lines. You can skip a few lines if you are comfortable. You can always do that. So will get cancelled. You will have 1. Now try putting n equal infinity. You will be having 1 by root over 1 plus 0 plus 1, which is 1 by 2. Okay, so before we were getting infinity minus infinity, but it turns out to be equal to 1 by 2. Okay, so be very careful about infinity minus infinity. So these are the few terms that you have to be very careful. 0 by 0. Okay, so whenever you have something like that, just know that you have to do something else first and then calculate the limits. Okay, third one. Okay, limit n tends to infinity. Okay, so how exactly do we find this limit? Okay, for example, if you put n equal 1, then you are having only one term. Okay, that is 1 by 1 by 2. If you put n equal 2, then 2, 3, right? But 2, 3 is already there. So if n equal 1, you will be getting this. N equal 2, you'll be getting 1 plus 1 by 2 dot 3. If you put n equal 3, then you'll be getting 1, 2. 1, because it should end in 3 and 4. Okay, you are looking at the last term. Okay, similarly, if you put n equal 4, n equal 5, n equal 6, okay, you need to look at the last term and then write the terms before that. Okay, so this you have to be very careful. Some of you may be trying to substitute n equal infinity over here, and then you will be having that this one is 0. You cannot do that because the term before it also depends on n. It may not look very clear that the term before this one depends on n. Okay, the term right before this one depends on n, but it does. Okay, even though they look like constants. Okay, but just know that depend on n. Okay, so that's why you cannot just substitute n equal infinity in the last term. Okay, but over here we will do some modifications. You will see this is actually a very interesting modification. Okay, the first term you can write it as 1 by 1 minus 1 by 2. Okay, if you simplify this one, you will be getting 1 by 1 dot 2. The second term, you can write it as 1 by 2 minus 1 by 3. Okay, 1 by 2 minus 1 by 3 will give you this. Okay, so again, the third term, you can write it like this. You can keep on going. 1 by n minus 1 by n plus 1. Okay, you can do this for all the terms. Now, what happens if we do it in this way? We see that these terms get cancelled, everything. Okay, minus 1 by 2 and plus 1 by 2 will get cancelled. Minus 1 by 3 and 1 by 3 will also get cancelled. Similarly, minus 1 by 4 with the next one will get cancelled. Everything will get cancelled, and even this one will get cancelled with the term before it. So the only thing that will be left is this first term, which is 1 minus 1 by n plus 1. So this is what we are having. 1, it is a constant, does not depend on n, and this one becomes 0. So the limit will be equal to 1. Okay, so we can do it like this. Okay, this is the final solution. And remember that whenever we are getting that the limit is equal to 1, 0, whenever it is a finite number, then we can say that the sequence is convergent. So indirectly, we are proving that the sequence is convergent by finding the limit. Okay, so whenever the limit is finite, that is, it is not equal to plus or minus infinity, then we say that, okay, the sequence is convergent. Okay, the fourth one, let's see, n tends to infinity. Okay, this is a bit different from the one before. If you notice, the difference is that over here the denominator is the same everywhere. Okay, so if you have the same denominator everywhere, okay, you can first simplify it in the usual way, and you will be having 1 plus 2 plus n. Okay, this one, it is an arithmetic progression. The sum of the first n terms, which is n plus 1 over 2. Okay, so if I have to write it down, you will be having this n square plus n. Again, we can take common. Now it has become a polynomial on top as well as on the bottom. So we can take common the highest power. You'll be having this by 2n square. N square and n square will get cancelled. So you'll be having, if you put n equal infinity, 1 plus 0 upon 2, which is equal to 1 by 2. Okay, so again, it is still convergent. Okay, because it has a finite limit. Okay, so this sequence is convergent. It converges to the limit 1 by 2. Okay, so now let us take a look at a harder one. Limit n tends to infinity, n power 1 by n. Okay, so this one, actually it is very difficult, because if you substitute infinity, you'll be getting something like this, infinity power 0. Okay, again, that is a term, that is an expression that you have to be very careful. Infinity to power 0, do not say that it is 1. Okay, you may be wrong, because it may not have a unique value. Okay, so how exactly are we going to do this one? If you remember back in your calculus course, when dealing with limits of functions, for example, limit x tends to infinity, x power 1 by x. Okay, whenever we are having something like this, okay, where it is very difficult to calculate it in the usual way, we will think of it in this way, okay, because n it is a natural number, okay, and it is natural number, it tends to infinity. So if n tends to infinity, then x tends to infinity as well, okay. Even if you take a real number x, it will be approaching infinity, okay. But the function has also changed from n power 1 by n, it has changed into x power 1 by x, okay. So the solution is we will calculate, okay, we won't calculate this one directly for natural numbers, but we will calculate it for x, okay. How exactly do we do that? Okay, we put y equal x power 1 by x, then we will take the logarithm, you will be having this. Now we will take the limit, okay, but still it is still x tends to infinity. So this is what we are having. The limit can go inside the logarithm, okay. Again, that was done in your previous classes, okay, in your lower classes I should say. And over here, just notice, if you put x equal infinity, you'll be getting log infinity, which is infinity, and over here also you'll be getting infinity. So this one, it is infinity by infinity. Whenever you have infinity by infinity, or sometimes you will be having 0 by 0, you will differentiate with respect to x, okay. You will keep this one as it is. Now differentiate the numerator with respect to x, and this one also with respect to x. This is possible because of a rule that you had learned, which is Lopitas rule. Okay, so this is what we are having. Okay, limit x tends to infinity of y. Limit x tends to infinity. If you differentiate log x, it will give you 1 by x. And if you differentiate x, it will give you 1. Okay, so we will be left with this. Okay, so if you notice, limit x tends to infinity of 1 by x, it is 0. Okay, 1 by a very huge number, it's equal to 0. Okay, but we want this limit, so therefore, okay, we will convert log into an exponential by taking its inverse, e power 0. So therefore, limit x tends to infinity. If you remember what is y, it's x power 1 by x, it's equal e power 0, which is 1. Okay, so therefore, okay, so it doesn't matter. If x tends to infinity, then n will also tends to infinity, and we will be having this. Okay, so those were the different procedures, I should say the different techniques how to calculate limits. Okay, but there are some limits that cannot be evaluated by the rules, okay, by the rule 1 or by using this kind of technique that we had just discussed. So for those kind of limits, we may need another rule, okay. This other rule, or I should say another theorem on limits, which is theorem number 4. I will write it down. Okay, it is called as the squeeze theorem or the sandwich theorem. Okay, so it states, the statement is like this: let xn, yn, and zn be sequences. Okay, and there are sequences which satisfies this kind of thing. Okay, it is like a sandwich. Okay, you have the bread xn and zn, and you have the meat or the salad in between. Okay, so you are squeezing this one by the two breads. Okay, let's see what is happening. If limit xn equal, okay, if the limit of the two breads they are equal, then the limit of the one in between will also be equal. Okay, so if you have to use sandwich theorem, okay, first of all you will take the middle sequence as yn. Okay, the sequence yn, it is the limit that you want to find. Okay, then we will construct, we have to construct our own sequences xn and zn such that this inequality is satisfied. Okay, and then we find the limit of xn, we find the limit of zn. Okay, if they are equal, we can just conclude that the limit of the middle sequence will also be equal to the rest of them. Okay, I will do this one. Okay, I will illustrate this one with the help of this example. Okay, question number 6. Find limit n tends to infinity sine n by n. Okay, this is different. It is not n tends to 0. Okay, if n tends to 0, then it is 1. Okay, but this is n tends to infinity. Okay, so how exactly do we do this? Okay, since we know that we are going to use sandwich theorem, we will take this one as yn. Okay, then, okay, the highest value of sine, the highest value of sine, it is 1. Okay, and the minimum value of sine, it is -1. Okay, so you will be having this. Okay, sine n by n, it's less than this. Okay, sine, it is always smaller than 1, and it is always bigger than -1. Or it can be equal also. That's why less than or equal to, less than or equal to. So this middle sequence, it's yn. This one, take it as xn. This one, take it as zn. Let xn equal -1 by n. Zn equal 1 by n. If we have to use the squeeze theorem, so we have first established this inequality. Next, we find the limits of these, of the outside part. Okay, the outside and the outside. Okay, so let me find it. So limit of this one, if you put n tends to infinity, it will be equal to 0. Okay, similarly, limit n tends to infinity zn, it will be equal to 0. So therefore, limit n tends to infinity xn, okay, the outside, okay, they are both equal. So if the outside are both equal, okay, and you are squeezing them because of this inequality, so the middle one also has no other choice but to converge to this value, which is 0. If suppose you are getting over here to be 1 and over here to be 1, then the middle one will also converge to 1. Okay, but since over here we are having 0, so that's why it will converge to 0. So by squeeze theorem, okay, yn, but yn it's sine n by n, it will be equal to 0. Okay, So you need to squeeze from the left as well as from the right and then calculate the limits. Okay, so the middle one will also have the same limit. If the limits of the outside parts are equal, then the limit of the inner one also will be equal to the limits of the outside parts. Okay, so that was question number 6. Now 7, it is also another one which needs squeeze theorem. Okay, this one may be a bit different. N plus n holding square. Okay, sometimes, okay, instead of n plus n holding square, they easily write it as 2n square, okay? 2n holding square, which is the same thing. And this one, notice that instead of n square, we can easily write it as n plus 0 holding square. Okay, by writing it as n plus 0 holding square, it gives us an idea of what is happening. N plus 0, n plus 1, n plus n. Okay, so the solution for this, since we know that we are going to use squeeze theorem, but also we have an idea that we can use squeeze theorem over here. Because you see that the denominators, they look the same, okay? They look the same, okay? It's just, but they are different, okay? It's just a very minor difference. Okay, if they are the same denominator, then we can easily add them up. But since they are not the same denominator, then we can use squeeze theorem. So we will take yn to be this whole thing. Okay, we want to keep yn in the middle, n plus n holding square. So we need to construct our own sequences xn and zn. Xn should be smaller than this. Okay, xn should be smaller. Now, which of these terms is the smallest from all of them? Okay, this one, this one, this one. Okay, you can easily tell that this one, it is the smallest because n is very huge in the denominator, which is n plus n. Okay, so that is why this is the smallest term. So we will replace everywhere with the smallest term, n plus n holding square. One by n plus n holding square. If you count how many terms are there, 0, 1 up to n, so we will be having n plus 1 terms. Okay, n plus 1 by n plus n holding square if you add them. And Zn, it has to be bigger than Yn. So that's why we will replace everything by the biggest term, which is n square. Which is equal to, okay, again we will be having n plus 1 terms. So n plus 1 by n square. This one we can actually write it down, n plus 1 by 4n square. Okay. So since we have replaced with the smallest term everywhere, therefore xn will be smaller or equal to yn, will be smaller or equal to zn. Okay, you can easily tell, okay, xn, this one will be smaller than this one will be smaller than this, and this one will be smaller than this. Okay, in fact they are equal, but everywhere it's smaller, so that's why it's smaller or equal. Similarly, if you compare zn with yn, this one it's bigger, it's equal to this one it's bigger than this, and this one it's bigger than this, so that's why zn will be greater or equal to yn. Okay, after doing this, okay, now we need to find the limit of xn and limit of zn, and we also need to find limit n tends to infinity zn. Okay, so xn it is n plus 1 by 4n squared, and Zn, it is n plus 1 by n squared. Okay, again over here what we can do, we can take common the highest power of n in the numerator by 4n squared. Similarly over here we can do it like this, by n squared. Or actually, okay, we can do this one another way. Okay, we can just split the terms. Over here we will be getting 1 by 4n plus 1 by 4n squared. Similarly over here we can write it like this, 1 by n plus 1 by n squared. Okay, this one is easier. Okay, so the limit, it will be equal to 0. Similarly this one will be equal to 0. So limit n tends to infinity xn equal limit n tends to infinity zn. So the outside parts, they are having the same limit equal to 0. So therefore the inside part, by squeeze theorem, will also be having the same limit. Okay, which is equal to 0. Okay, so this completes our solution for finding the limit of yn. Okay, another example which is a bit different from the rest. Okay, but I think I should do this. If x1 equal root 2, xn plus 1 equal 2 root 2 xn, then find limit n tends to infinity xn. Okay, so the solution, we just need to use this one. Okay, so xn plus 1, it's given in terms of xn. Sometimes instead of xn plus 1, you can also have xn plus 2 or xn plus 3. Okay, it's written in terms of the other terms. Then this is the technique that we will follow. Just use that equation, that expression that you are given. Okay, we can square both sides, which is 2xn. Okay, now what will we do? Okay, we can write this one like this. Okay, so after writing it in this way, now we will take the limit. Okay, 2, it is a constant. You can take it outside of the limit. It won't influence anything. And limit of 0, it's 0. So I'm writing it directly. Now, this is the crucial part. Okay, since we need to find limit n tends to infinity of xn, actually that is the first step. Okay, let limit n tends to infinity xn, it's equal to x. Okay, so over here you can easily write minus 2x equal to 0. But what about the limit of this one? Okay, just think, okay, x1, x2, x3, so on, xn, then you can also have xn plus 1. If xn converges to x, okay, because xn plus 1, okay, if you put n equal to infinity, okay, it won't matter, right? If you put n equal to infinity, it will also converge to x. Okay, similarly xn plus 2. Okay, if you put n to infinity, it will reach, I can think of it as the last term or something like that. Okay, so it will always converge to x. So that's why if xn converges to x, xn plus 1 whole thing square will also converge to x square. Okay, so this is what we are having. So now we just need to solve them. x minus 2 equal to 0. Okay, but this one, it's impossible. Okay, it is impossible, because if you see x1 it's equal to root 2, okay, x2, okay, and then we're having this formula xn plus 1 equal root 2xn, right? Okay, now just think, if you put n equal to 1, you will be getting x2 equal to 2 root x1. Okay, so again it's not equal to 0. If you calculate x3 by using this expression, you'll be getting root 2 x2, which is 2 x2, it's root 2 root 2 again. Okay, so everywhere it's not equal to 0. Okay, so that is why. Okay, and it won't converge to 0. Okay, if you see the pattern. Okay, because it is actually increasing, right? This x2 it's bigger than x1, x3 it's bigger than x2. Similarly, if you calculate x4 according to this formula will be equal to 2x3, but x3 has been given by this. Okay, so if you notice, it keeps on increasing. x1 started with root 2, the sequence keep on increasing, so that's why the limit won't be equal to 0. So that is why x will be equal to 2. That is, limit n tends to infinity, xn will be equal to 2. Okay, so with this I complete this topic today about using the theorems, that is the three theorems plus the sandwich theorem. Until next time.